Today I am going to be talking about a project that we are doing in collaboration with the Big Learning Research Group on campus. So that includes Eric Jing and Garth Gibson and their students. And I'll be talking about measuring performance of big learning workloads. So big learning, it's defined as large-scale machine learning on big data. So large-scale machine learning is models that are have a lot of parameters that need to be learned, that take up a lot of memory. Sometimes you distribute those parameters across multiple compute nodes. And it also has to manage not only that distribution of parameters, it has to manage large amounts of data, not only to train these models with, but to use them. The landscape, to say the least, is dynamic. My collaborator, Garth, estimated or counted 2 years ago over 1,000 papers published in the area of machine learning. That number's only gotten bigger. There has been a deluge of new and larger data sets to enable applications in speech, translation, image classification, the standard stuff. And because these systems are getting larger and larger, the hardware platforms are getting more and more complex. The algorithms are getting more and more complex to deal with that. And there's been this explosion of computing platforms. So that's the center of this slide. Things like Spark have been around for a while. They have a library on top of it called MLlib that does machine learning. But there's been just releases in the last year from Google with TensorFlow. Microsoft and Amazon are getting in the space of providing machine learning as a service on their cloud platforms. The systems hardware are complex. So measuring performance is no simple thing. In this space, not only do you have the traditional measurements like Ed Morris was talking about of precision and recall, and also drift when using it. You have performance of the hardware itself. So traditional HPC performance, how many flops am I getting out of the system? Is my memory bus saturated? Am I spilling out of memory? Am I using disk in the most efficient way? So there's a lot to measure in these systems. So this project, part of it was to build a tool that can actually capture any or all of these metrics. So I already said about the 1,000 papers and growing. Ed also said that reproducibility is a challenge. So because these systems are so complex, in a research paper you can't possibly give everything that you would need to actually reproduce one of these results. And we're here trying to help not only measure them, but what is important to measure so that we can speed up adoption of new technologies in this space for DoD. And so if we can do this, we can also improve reproducibility. And let me show you how. So the first step was to actually design a big learning platform. What you see here is what we stood up with campus. So this cluster is actually bought partly by the SEI, the government, and it's housed and managed by the Parallel Data Lab on campus, and has enabled a tremendous amount of research by the students over on campus and the researchers. It currently has 42 compute nodes. Each one of those nodes has a multi-core processor. It has an extremely complex storage, tiers of storage, so it has 64 gigabytes of RAM. It has 400 gigabytes of SSD, and that's backed by 8 terabytes of hard disk on each node. And that's just to do computation when training and using these models. It also has a GPU accelerator. That's actually extremely important in the era of deep learning. There's plenty of platforms, compute platforms out there that leverage GPUs to do deep learning in a fast way. Off to the side is persistent storage. So we have 400 terabytes of raw storage that we store data sets on. We also store the machine learning models that we're training. Those need to be off the compute nodes because everything on the compute side is ephemeral. I'll explain why in a minute. And connecting all of these things is a very fast, low latency, 40 gigabit per second network. So what we did was survey the space for measuring performance in the traditional HPC space. We already have the expertise on campus on how to measure performance in machine learning and trying to put this all together. So on the right and in the lower part of the middle is the hardware. So we have the persistent storage and the compute cluster. On the left and above are the services that have to run in the data center. So we have an OpenStack instance that is managing our collection system, which we call Performance Measurement Workbench. We chose the ELK stack. It's now been renamed Elasticsearch. It has Elasticsearch, Logstash, and Kibana. So Logstash is a way to transform and load data into the Elasticsearch database. Elasticsearch manages the database and manages queries on the data that's in there. And Kibana is really the query front end, so you can visualize data. We added something else called Grafana because we found that Kibana's visualization stuff was kind of hard to deal with at the scale of the metrics that we're trying to visualize all at the same time. Grafana actually gives you a graphical interface which enables you to distill a lot more information. With that, we also provide an operating system that's already got pre-installed a couple of tools that we need. So, and these are pretty standard open source. The first one is CollectD. That one's already been available for a long time. It knows how to get at the system metrics like CPU utilization, memory, disk, and network. We added FileBeat, which is a way to just, we can configure it to basically pick up any file that's output on the system and ship it across to Logstash. And that way we can actually instrument machine learning workloads. So add that to the mix. We also want to make this easy for the user to do, but we did have to impose one thing. They do need to instrument their machine learning applications. There's no standard way to have a machine learning application report its performance. Well, there's no standard machine learning application. And so we've provided through FileBeat a way for them to just output log messages to a file that FileBeat's been pre-configured to ship across on a periodic basis. So what does this look like for the user? We created a front-end portal. They log in. They configure their machine learning job. They select the number of compute nodes they want on Orca. They select the compute platform, say Spark or TensorFlow or a research platform that they're working on right now. And they say go. Our portal talks to Emulab. Emulab is a service running in the parallel data center, and it does bare metal provisioning. And that's the reason to do bare metal provisioning is to get the most performance out of your hardware possible. What it means, though, is that you pick your OS, and Emulab actually installs it on the compute nodes and boots those nodes, and then they become available. So the portal integrates with Emulab and basically requests the nodes and waits for them to spin up and then submits the job onto the nodes that were allocated. So that's this step. Now, while the ML application is running, the user has the option to visualize what's going on live because CollectD and Logstash are always shipping diffs to the log files back over to Logstash and being loaded. You can do a continuous query to the data for this experiment and provide a live dashboard if you'd like. I'll show that in a second. But also, since everything's stored in the database, you can do post-mortem analysis. You can see the entire dashboard for the experiment after the fact. You can actually perform other queries on the data to get at what's really going on in the system. And so this is an example of one dashboard. So this is a logistic regression machine learning application running on Spark. So this particular experiment requested 8 compute nodes with 8 worker nodes with 1 master node. So it's a 9-node experiment. We discovered in Spark that the master node behaves very differently from the worker node. So we created a display that separates the two. We expect all the worker nodes to do the same thing. The worker nodes are on the right. The master or head node is on the left, and you can see a vastly different performance profile. The top line would be CPU utilization. The second line is memory. The third is disk I/O, and the fourth is network, if I can read that correctly. A lot of information just for system metrics, so what I consider traditional HPC metrics. What's also on here, it's a little hard to see, are these little vertical lines that are going through the plots all at the same time. Those are actually discrete events that were emitted by the logistic regression application just to prove that we can pull data out of the ML app. There are 4 or 5 phases to this computation. You load training data, you perform a fit for the logistic regression model, then you load the test data, and then you perform a verification or validation or an accuracy measure on the resulting thing. So you can see those with some vertical lines there. There's a very long validation phase at the end where all the worker nodes are performing at peak. What the students really like is being able to query across multiple experiments. So the standard thing in large-scale machine learning is scaling plots. So this is a weak scaling plot of 4 experiments with 2, 4, 8, and 16 worker nodes. It's showing that we can query phase times for logistic regression and collate them into one plot. And this is generally what you would put into a research paper. So to wrap up, I want to revisit something I said at the beginning, which is reproducibility. It's very, very difficult to do in this space. We can collect a tremendous amount of information about the experiment with this current setup. So through the portal with user requests, we know the complete operating system image that was used. And we know what was installed in that operating system, packages, version numbers, things like that. We know which ML platform they requested, and we know the version number and things like that. But not only that, we know the command line that was used to invoke it. Spark has thousands of command line options that you can use to tune that thing. That makes it very hard to repeat Spark experiments. It's generally not reported completely in the literature. We know the code, or at least the command line for the machine learning application that the user ran. And we know the data set that they wanted to load. There are a few things that we don't collect right now that we could maybe get at, but it requires some curation. We don't know the specifics about the hardware unless it's input into the database. And especially, we don't know what firm level things are at. But at a good data center, you're tracking all that anyway in another database. We don't have version control of the application code that was done, but version control of code is pretty simple. That could be integrated into the system. The one thing that we can't do with this system is basically data set version control. When a data set is 100 terabytes to begin with and a change to it, it gets a little unwieldy. So with that, I'll ask if there are any questions. Go ahead.
Wow, this is almost the perfect segue to the last set of questions, so thanks.
No problem.
Okay, step 1, get together with Ed.
Check.
Scott was on that team to start with.
Yeah. So
Awesome.
I was there early on.
All right. Number 2. So yeah, I think an extension of Ed's final comment was that the kind of V&V we're doing on the algorithm should extend to the infrastructure supporting the algorithms, right?
Yes.
And so this is an awesome example of that. If we can create this as a service, right? We can
Sure.
make what you're doing a service, whether it's part of the deployment, Docker package that gets pushed out, or it's, somehow attached afterward. That's, I don't know.
Yeah, right now it's an
Design choice.
OpenStack instance, so
Right.
we can just package it up.
So that's a perfect segue to the next question. So we have sort of an emerging technology now where basically you have infrastructure as a service. And two big exemplars, which are part of the upcoming 5G standard, or at least candidates for it, are software-defined exchanges and software-defined networks on top of things like self-organizing network, down to the physical layer type infrastructures, right? And so you can envision a world where you're essentially buying bare metal as a service and deploying everything else. So the question is, do you have a vision for how to create the master wrapper for all of that, right? Put it all together and then doing online deployment of everything on demand in your new cloud environment, and then allowing the user to monitor its performance until you throw it away and do something else. And you don't have to answer all of that. Just philosophical response would be fine. Thanks.
Is there one silver bullet? Is that one of the questions?
No, I'm just trying to get a strategic perspective on how you go there, like thoughts.
This is a good first step. I mean, there are a lot of pitfalls in trying to set something like this up, and what we found is I don't know if we can get away from dependency on the particular hardware configuration. So you were talking about software-defined X and things like that. In order to figure out how to report how something behaved when your network is dynamically reconfigurable, well, you're going to have to capture that entire thing. I don't know how to put hooks into everything yet. But if there's a way to put a hook into it, FileBeat can put it in the database.
So the SDX standard actually provides for that,
Okay.
But not completely.
Yeah.
And it's an evolving standard. So there's a leverage point I think you could use. And the other, on the flip side of how do you configure yourself depending on what hardware you find yourself on. I mean, your last talk yesterday was about self-configuring, HPCs, right? LMS, like the future,
Yeah.
right?
Yeah. There's a play in software-defined hardware there.
Right, exactly. So if we can get to the point where we can dynamically learn the HPC and then deploy and then verify, I think that's kind of the future.
Yeah.
So,
The bottom line is you need to measure everything.
amen.